Hello students, welcome back to our channel. Students, in this video we are going to study a very important topic from class 12th physics, chapter wave optics. And this topic is Young's double slit experiment. There are many different types of questions that can be made from this topic. There is an important derivation in this topic, 4 or 5 very important formulae, a very important diagram, and there are different types of conceptual questions that can be made based on this topic. So overall this topic is very important. Let's start. What is Young's double slit experiment? This is an experiment which was carried out by a scientist whose name was Young to demonstrate the wave nature of light. It was carried out in 1801 and Young wanted to show the world that light is a wave. So how he did that? Let's start. This is a setup. We will come to this, but let's first study this with the help of this diagram. Why this experiment is called double slit experiment? Because two slits were used in this experiment. What is a slit? Slit is a very minute hole, but it is different from hole. The shape of the slit is like this. This is a hole, right? But of this shape. ये जो लंबाई में है, this type of hole is called a slit. So there were two slits. So what was the role of those slits? For that, first we have to understand the concept of the interference and coherent sources of light. What is interference? Interference means when two waves superimpose on each other. Let us say we have two waves. The pattern of one wave is like this, and the pattern of other wave. Okay, I'll copy this part. Let's save some time. Okay, one wave is like this. One wave is like this. And second wave is like this. Now, if these two waves superimpose on each other, what will happen? If these two waves superimpose on each other, now let's make the resultant wave here. So if these two waves will superimpose on each other, then the crest of this wave is going to fall the crest on the crest of this wave, right? And the trough will fall on the trough. So what happens? The resultant intensity of the wave, which is formed after the interference of these two waves, will increase. So it will look like this. Right? So this is called the interference of wave. This is one way for waves to do the interference, but there can be other patterns also. Suppose this wave is like this and the second wave is like this. Now if these two waves interfere, so the crest of this wave is going to fall the trough of this wave, and the trough of this wave is going to fall on the crest of this wave. So what happens? They are both going to cancel their energies and the resultant wave will disappear. If, let us say, the amplitude, you must know the basics of waves, only then you can understand this topic, Young's double slit experiment. Now let us say the amplitude of this wave is A and the amplitude of this wave is B, and let us say B is greater than A. Let us say B is greater than A. So what happens? Some part of this amplitude will get cancelled by this, and there will be a small wave which is left here like this, right? And if the amplitude of A and B both are equal, if B is equal to A, so what happens? You will not get any wave. So why is this happening? Because wave is simply a disturbance in the space. So if this disturbance is going like this, then when this disturbance is reaching here, it is making the particles of this region to go in the upward direction, but this is a disturbance which is, when reaching here, is making the particles of this region to go in the downward direction. Now what happens if these two disturbances reach simultaneously at this particular point? So one will say to the particle that go up and the other will say to go down. So who will win? The disturbance with more energy will win, right? So that's why we are saying that if B is greater than A, there will be a small part left here. Otherwise, if A and B are equal, there will be no wave. So this is called the interference of waves. Now, in case of Young's double slit experiment, Young needed two coherent sources to achieve the results. Now, what are coherent sources? Coherent sources are coherent sources are two sources of light which produce the light of same frequency, same wavelength, and with a constant phase difference, right? So no two different light sources can be coherent, right? Two coherent sources are those sources which are producing ekdam identical light. They are producing or they are emitting the light of same wavelength, same frequency, and with a constant phase difference. So Young wanted two coherent sources of light. Why he wanted two coherent sources of light? Because if there is some phase difference, what is phase difference? What is phase difference? Now, if one wave is like this, one wave is like this, and one wave is like this, so we will say that there is no phase difference between these two waves. I'm not going into the details of the waves because that will make this video very long. So, as I said, you must know the concepts of waves if you want to study Young's double slit experiment. Now, let us quickly revise what is phase difference. Now, this part of the wave is the zero phase. This is 90. This is 180. This is 270. And this is 360. Now, if you compare these two waves, the zero of this wave is lying here and the zero of this wave is also lying here. The 90 of this wave is lying here and the 90 of this wave is also lying here. 180 of this wave is here, 180 of this wave is here. So there is no phase difference between these two waves. Now, if the waves are like this, if the waves are like this, one wave is this and the other wave is this. Now we will say that there is a phase difference of 180 degree between these two waves, because here is the zero of this wave and this is the 180 degree phase of this point of this wave which is at 180 degree phase. So if we compare the pattern with this wave, we will say that this point is here, right? So the point of 180 degree phase is exactly at that point where the 0 degree phase point of this wave is. So there is a phase difference of 180 degree between these two waves, right? So there are different phase differences between the waves. Now, if the phase difference between the waves is not same or not constant, the whole experiment of Young was based on this fact that he is going to interfere those two light waves. So what happens? We will get a pattern of alternate light and dark bands on the screen. So why we are getting this pattern? Because there will be some points where the crust of one wave is going to fall on the crust of the other wave, and there are some points where the crust of one wave is going to fall on the trough of other wave, and there are other points also where some part of the crust is going to fall on some part of the trough, and the overlapping will not be uniform. So what happens? We will get a pattern like this. We will get a pattern like this if these are two coherent sources. So why we need two coherent sources? I'll just explain. These are two coherent sources of light. So if they interfere, these are the region. This middle line is exactly the region where the crust of one wave is falling on the crust of other wave, and the trough of one wave is falling on the trough of other wave. And these dark lines are the regions on the screen where the crust of one wave is falling on the trough of other wave. So we are getting a dark band because both the waves are cancelling each other. And here we are getting a light wave because the intensity is increasing. And in between light and dark waves, there are points where some part of the crust is falling on some part of the trough. So that part of the screen is neither very dark nor very light. But for this, we need two coherent sources of light. Why? Because if the phase difference between these two waves are continuously changing, suppose this wave is like this, and in fraction of second this wave becomes like this, and in fraction of second this wave suppose becomes like this. So what happens? These two waves will interfere. If the phase difference is not constant, still these two waves will interfere. But what happens? The pattern of light dark bands on the screen is not going to be fixed. It will be continuously changing, and it will be changing so rapidly, then we will not get any pattern. So to get a sustained interference pattern, coherent sources were needed, right? And since coherent sources emit identical light, so no two different sources of light can be coherent. So that's why he used two slits, because he used a single source of light. Here he had a single source of light, and that source emitted light, and that light passed through this obstacle where he had, I was not there at that time, where he had two slits, and those two slits, since they were emitting the light of a common source, so those two slits can be considered to be coherent, because now they are emitting the identical light, right? So the light is coming from this source, and these two sources are emitting identical light, and that light is interfering in this region, and a pattern of light dark bands is formed on the screen. So based on this pattern, Young suggested that the light should be a wave, because the explanation of this pattern was based on the interference of waves, and obviously the interference is the property of waves, and light is showing this pattern which is based on the interference of waves. Then obviously the light is also a wave, right? So there was some mathematics involved in this. So let us discuss those points. So we should remember two terms here. One is the coherent sources of light, and second is the monochromatic light. Monochromatic light is a light which consists of a single wavelength. White light is not monochromatic, because white light is made up of 7 different types of colors, and by color we mean wavelength. If red color is different from green color and green color is different from violet color, it's because their wavelength is different. So white light has 7 different colors, which means it is not monochromatic. Mono means one, chromatic means color. So light which is made up of one color, and light which is made up of one color consists of a single wavelength. Such type of light is called monochromatic light. So let us say the equation of this wave which is coming out from this slit is, now this is what? This is a view of top part of the setup, right? This is the top view. So if this is the front view, these two are the slits, and a coherent source is kept here. So if you look this from here, top view, you will get a picture like this. So first wave is y1 equal to a, first wave is y1 equal to a sine omega t, and second wave is y2 equal to b sine omega t plus phi. Now these two waves will interfere, and a final pattern will be formed. So how is this going to happen? So we have taken the amplitude of first wave as A and the amplitude of second wave as B, and the phase difference between these two waves is phi. So what happens? These two waves will interfere, and the resultant amplitude or the displacement will be y1 plus y2. So y1 was a1 sine omega t, and y2 is a2 sine omega t plus phi. Now this is a1 sine omega t. Now here we will apply a formula of sine a plus b. So a2 sin omega t cos phi plus a2 cos omega t sin phi, because the identity of sin a plus b is sin a cos b plus cos a sin b. So we have applied that identity, sin a cos b plus cos a sin b. If you take sin omega t common, if you take sin omega t common from these two, this has sin omega t and this has sin omega t. Now if you take sin omega t common, here we are left with a1 and here we are left with a2 cos phi, and this remains like this. Now let us put a1 plus a2 cos phi as r cos theta. We don't know what is r, we don't know what is theta, but let us put these values here, then we will get to know what is the meaning of r and cos theta. And in place of a2 sin phi, let us put r sin theta. So this becomes r cos theta sin omega t plus r sin theta cos omega t. So if we take r common, so this is again an identity of sin a plus b, sin omega t cos theta plus cos omega t sin theta. So sin a cos b plus cos a sin b, which is sin a plus b. So this becomes sin omega t plus theta. So this is okay. Why we did these substitutions? Because we know that after the interference of wave, what we will get? A wave. Obviously the interference of waves is going to produce a wave, and the equation of a wave looks something like this, but the interference equation of these two waves was looking like this. So we want to see what is the amplitude of the resultant wave, what is the phase difference of the resultant wave. So to find those quantities, the wave should look like a wave. The equation of the wave should look like the equation of a wave. So after doing this substitution, now see, this equation is r sin omega t plus theta. This equation is r sin omega t plus theta, right? Okay, so and this obviously looks like the equation of a wave. So what is this? This r is the amplitude of the resultant wave. This r is the amplitude of the resultant wave. And what is r? So we can find the value of r using these two equations. If we square and add these two equations, what we will get? We will get r square cos square theta plus r square sin square theta equal to square of this plus square of this. So square of this plus square of this. Now a plus b whole square is what? A square plus b square plus 2ab. Right? So a square plus b square is a2 square cos square phi, and 2ab is 2 into a1 a2 cos phi. But since we have this this was not sin phi, this is a2 sin phi, right? This is a2 sin phi, so this is the square of a2 sin phi. This is the square of a2 sin phi. So a2 was common in sin square phi and cos square phi. So we took a2 common, and sin square phi plus cos square phi is nothing but 1. So we are left with a1 square plus a2 square plus 2a1 a2 cos phi, and that is the value of what? This was the value of what? Take r square common on the left hand side, and bracket में बचेगा cos square theta plus sin square theta, which is 1. So this is the value of r square, right? So r square is this. So r becomes what? Which is the amplitude of the resultant wave? R becomes under root a1 square plus a2 square plus 2 a1 a2 cos phi. So that is the resultant amplitude of the resultant wave, which is formed by the interference of these two waves, and that depends on the amplitudes of the two waves and the phase difference between the waves, right? And intensity of any light is always proportional to the amplitude, square of the amplitude. And since the amplitude of this resultant wave is r, so what is the intensity? Intensity is proportional to r square. So we can say, iska square karo, root hat jayega. So we can say I is proportional to this. And since A1 square is what? Obviously the intensity of first wave depends on A1 square. Or we can write I1 is proportionality का sign हटा के constant apply किया, so we can write it like this. I2 is proportional to A2 square. So I2 is K A2 square, and this I is K R square. So if you substitute all those values, you are going to get this. So this is the formula of the resultant intensity, which is based on the intensities of the individual waves. Okay, what is constructive interference? When the crust is falling on the crust and trough is falling on the trough, and we are getting a light band where the crust is falling on the crust and trough is falling on the crust. That interference is called the constructive interference, where the resultant amplitude is maximum. And the value of this R depends solely on the value of cos phi, because A1, A2 are going to be constants. So when cos phi is 1, which is the maximum value of cos theta, obviously then R will be maximum. So cos phi is 1 whenever phi is the even multiple of pi, right? This is the case whenever there is a path difference. What is a path difference? What is a path difference? Like this is the setup of the Young's double slit experiment. This is source S1 and this is source S2. Now suppose here we have a general point P. So the waves reaching at this point are like what? So the waves reaching at this point are like this. Suppose this is 1 wave, 2 wave, 3 wave and 3.5 waves. 1 wave, 2 wave, 3 waves, 4 waves and 4.5 waves. So we will say that the difference in the paths of these two waves is lambda, because now here we have 4.5 waves and here we have 3.5 waves. So one wave is less in S1P. So S2P minus S1P is lambda. So this S2P minus S1P for any point P is called the path difference. And obviously what type of band is going to form at P depends on this path difference. Since now the path difference is lambda, then obviously the crust is going to fall on the crust at this point. So we will get a light band. Right? So whenever the path difference is a multiple of lambda, whenever the path difference is a multiple of lambda, or the phase difference is a multiple of 2n pi, because when the phase difference is 2 pi, there is one wave shorter. When the phase difference is 2 pi, there are 2 waves shorter. When phase difference is 6 pi, there are 3 waves shorter. Obviously whenever the phase difference is the even multiple of pi, पूरी एक wave छूट जाएगी और interference होगा. So that's why when the phase difference is 2n pi, we are going to get a light band and the path difference is lambda. But there is a general formula, there is a general relation between the phase difference and the path difference. Since whenever the phase difference is 2 pi, the path difference is going to be lambda. So whenever the phase difference is 1 radian, the path difference is going to be lambda by 2 pi. And whenever the phase difference is phi, the path difference is going to be lambda by 2 pi into phi. This is the path difference. So if you know the phase difference is 2n pi, just put 2n pi here and 2 pi will get cancelled out and the path difference will be n lambda, which means that whenever the path difference is an integral multiple of lambda at a particular point, then we will get a light band at that point, right? So the path difference is n lambda. Now what is destructive interference? Destructive interference is where the dark band is forming, right? Where the crust is falling on the trough and trough is falling on the crust and they are both cancelling each other. So in case of destructive interference, R has to be minimum. In case of destructive interference, R has to be minimum. And R is minimum when cos phi is minimum and the minimum value of cos phi is -1, which is when phi is 2n plus 1 into pi. And the path difference using that formula that was written in the previous slide is x equal to 2n plus 1 into lambda by 2. So these are the conditions of constructive and destructive interference. Very important conditions. I was talking about 2-3 important formulae in the beginning of the video, and now we are discussing all those formulas. So these are very important formulae, and many numericals are based on these concepts. Ratio of intensity of maxima and minima. Okay, what is R max now? Maximum amplitude is what? R max. R max is what? R max is under root, when cos phi is 1, so it is under root a1 square plus a2 square plus 2 a1 a2, which is simply a1 plus a2 ka whole square ka root, which is going to be a1 plus a2, which is going to be a1 plus a2. So this is R max. Similarly, what will be R min? Minimum amplitude is when cos phi is minus 1. So this is a1 square plus a2 square plus 2a1 a2 cos phi, which is minus 1. So this is nothing but under root a1 square plus a2 square minus 2a1 a2, which is a1 minus a2 square, which is a1 minus a2. So obviously, in case of constructive interference, crust is falling on the crust and trough is falling on the trough, so the amplitudes get added up. But in case of destructive interference, their amplitudes are in opposite direction, so amplitudes will be subtracted. So this is R max, maximum amplitude, and this is the minimum amplitude, and intensity is directly proportional to the square of the amplitude. So I max is proportional to the square of this, and I min is proportional to the square of this. So this is again a very important result in Young's double slit experiment. Right? Ratio of intensity of light due to two sources. Obviously, their ratios of intensities are I1 by I2 equal to A1 square by A2 square. Right? The ratio of the squares of their amplitudes. And the intensity ratio is obviously directly proportional to the slit width. If the slit width is more, then obviously more light is going to enter through that slit. So intensity of the light is directly proportional to slit width. It is also directly proportional to the square of the amplitude. So combining all these, we will get W1 by W2, which is the ratio of the slit widths, is I1 by I2 is equal to A1 square by A2 square. There was another very important derivation now, which is not in syllabus anymore, which is the derivation of the slit width. Sorry, not the slit width. It is the derivation of the fringe width. These light and dark bands are also called fringes. These light and dark bands are also called fringes. So the width of one fringe is lambda d by d, where lambda is the wavelength of the light used, capital D is the distance between the slits and the screen, and small d is the distance between the slits. Right? Okay. There is one important point to be noted, which is energy consideration. There is a small derivation in which we show that the total energy remains conserved. The energy is just being redistributed. Before the interference, the energy was uniformly distributed, and after the interference, there is a non-uniform distribution of the energy. But overall, the total energy remains same. So the total energy before interference was what? By energy, we mean intensity. Obviously, intensity is a way to measure the energy of a wave. So the total energy before the interference was I1 plus I2, which is obviously because I1 is proportional to A1 and I2 is proportional to A2. Let us say that A1 is A, the amplitude of the first wave, and A2 is B, which is the amplitude of the second wave. So we can say that I1 is proportional to A square and I2 is proportional to B square. So I1 is Ka square and I2 is Kb square. So I1 plus I2 is K into A square plus B square. So this was the intensity before the interference of the light. Now after interference, the energy gets redistributed. So how we will find the intensity now? We will just find the average of the minimum and maximum intensity. Minimum intensity was what? Minimum intensity was A minus B whole square and the maximum intensity was A plus B whole square. So I max plus I min by 2, that is the average after the interference, which is, let's take K by 2 as common, A plus B whole square plus A minus B whole square. Now expand this using the identity of A plus B whole square. So if we expand this, we will get A square plus B square plus 2AB, and if we expand this, we will get A square plus B square minus 2AB. Now this 2AB and 2AB will get cancelled out, and A square plus A square is 2A square, and B square plus B square is 2B square. Taking B common and these 2's get cancelled out, we will get this intensity as K into A square plus B square, which is again same as the intensity before the interference of waves. So there is just the redistribution of energy, but there is no loss or gain of energy. So energy remains conserved in this experiment, right? So that is what we had to prove. So this was all these derivations are very important. All these results are very important. The diagram of Young's double slit experiment is very important, and the derivation is also very important, and you can get different types of numericals based on all these formulae that we have studied in this video. I'll meet you in the next lecture. Till then, all the very best.